Any questions before we keep talking about radiation? All right. So we finished on Wednesday. We talked about the properties of radiation, mostly going through concepts, and we said that kind of the most important things to remember about radiation are radiation is emitted from surfaces and is also incident upon surfaces. And radiation can be emitted over a range of wavelengths, and also radiation emitted from a surface is emitted in all directions that are described by a hypothetical hemisphere above the surface. And we said to describe the directional effects, we're going to make use of the spherical coordinate system. So we need to account for the fact that radiation is emitted over a bunch of different wavelengths and a bunch of different directions. And so to get the total emissive power, you have to integrate that up over all of the wavelengths and directions. So we were talking about directional effects in the context of the radiation intensity concept. Which we just briefly started on. And first, we're going to go through some geometric definitions to kind of set up the way we're going to handle these directional effects. Okay, so we should all be familiar with a plane angle, right? It's just the typical angle in degrees or radians that we talk about, and it's usually defined as a portion of a circle. So for radiation, we're going to use the solid angle. So we'll write down the definition of the solid angle. And we'll talk about a differential solid angle to start with. So the differential solid angle so instead of being defined like a plane angle, a plane angle is defined by the region between the rays of a circle, and a solid angle is defined by the region between the rays of a sphere. And I'll show a schematic in a minute to kind of clear that up. So the differential solid angle is defined by a region between the rays of a sphere and again, instead of drawing this, I'm going to show you the schematic from the book. So here you can think of this as the center of a sphere, and then these are the rays pointing out in a conical shape. And the solid angle is the angle right here. And it's defined as the ratio of the surface area on the sphere that is intersected by these rays divided by the radius squared. Hopefully familiar from math, yes.
So do we not care about the curvature, or is this sufficiently small that there is?
Great question, yeah. So because it's a differential angle, it's really, really small, so you can neglect the curvature. So we'll actually show in a minute when we're talking about radiation coming out from a point on a surface and hitting a hemisphere, the differential area that it passes through in the hemisphere is actually a rectangle because the curvature can be neglected because it's such a small angle. Okay, so the definition then is this differential solid angle, d omega, is the ratio of the surface area that is intercepted by the rays, dA sub n, over the radius squared. And this dA sub n is the surface area on a sphere. And then r, of course, is the radius. So we're going to consider radiation emitted just from a point on a flat differential area in a certain direction defined by the angles theta, which tell you kind of the direction in, I think, the zenith direction, and then the azimuthal direction, phi. And I'll show you a schematic of that too. So consider radiation emitted from a single point on a differential surface dA1 in a certain direction in the spherical coordinate frame. And that direction is defined by the theta and phi angles. So that's going to look like this. Okay, so we've got the differential surface area, dA1. There's radiation being emitted from a certain point on that surface area in a direction that's defined by this angle theta and the angle phi. And the hemisphere is drawn at a certain radius, r, from this differential area. And so this hypothetical hemisphere drawn at the radius r, the radiation leaving from this point, going in this direction, is going to pass through this differential area on the hemisphere, dA sub n. And it's going to kind of pass through this solid angle as well. And like we said, because curvature effects are negligible, because we're talking about differential angles and distances, the area that it passes through on the hemisphere is going to be a rectangle. And the rectangle is given by r squared sine theta d theta d phi. And we'll write this down too. And that's just, you can derive that from the geometry. And I'll include all these figures with the notes when I post them online. Okay, so the radiation passes through a differential area, dA sub n. That is on the surface of a hemisphere at radius r from the point of emission. And then the surface area is given as dA sub n equals r squared sine theta d theta d phi. So if we look at our definition of the solid angle, for this case, the solid angle is going to be just the area divided by r squared. So that's sine theta d theta d phi. So we know radiation is emitted in all directions defined by a hemisphere. And that corresponds to phi going from 0 to 2 pi. So that's kind of all directions this way. And theta from 0 to pi over 2. So a full sphere would be theta is 0 to 2 pi as well. Seems like that should be pi instead of pi over 2, but I'm pretty sure it says pi over 2 in the textbook. Anyway, not super important. I'll double check. So if we integrate the solid angle over this hemisphere, we get that it's equal to 2 pi steradians, where a steradian is the unit of the solid angle. And this makes sense because a sphere measures 4 pi steradians, so a hemisphere is just half of that. So this is kind of just to show you how we account for radiation emitted in all the different directions that we're integrating up over this solid angle. And to account for directional effects, we have to integrate up over the solid angle that defines a hemisphere, which is 2 pi steradians. And we do that by integrating from phi is 0 to 2 pi and theta 0 to pi over 2.
Can you define or can you spell a steradian?
Sure.
Thank you.
Hopefully this was like calculus 3 or something. No? No? Okay, cool. Shouldn't have to worry about it too much. I just wanted to show you kind of where the concept of the solid angle came from, because we're going to talk about this d omega a little bit. Okay, any more questions about that? So it's definitely pi over 2 in the theta direction. Yeah, yeah. Okay. All right, so for heat transfer, we're always curious about the rate of things. So we're going to talk first about the rate of emission, specifically the rate of heat transfer. So we're going to talk about the rate of emission, and the reason we introduced this kind of hemispherical and differential area concept is because we first talk about the rate of heat transfer as kind of as far as how fast heat emitted from a certain point is passed through that differential area in the hemisphere. Okay. So we'll talk about emission first, and then consider irradiation. So we're going to say, consider the rate at which emission from a differential area from dA1 passes through the corresponding differential area on the surrounding hemisphere, dA sub n. So consider the rate at which emission from dA1, this differential area on a surface, on an emitting surface, passes through dA sub n, which is the corresponding differential area on the surrounding hemisphere. This rate is defined in terms of the spectral intensity. This is a pretty important quantity, and so we're going to write out fully how it's defined. So the spectral intensity, I sub lambda comma E, and this subscript E is for emission. So there's a different spectral intensity for emission and irradiation. So we're talking about emission specifically right now. So the rate at which radiation is emitted from dA1 and passes through dAn is defined in terms of the spectral intensity. And this is a bit of a long definition. So the spectral intensity is the rate at which radiant energy is emitted at a given wavelength, lambda, in a given direction, defined by theta and phi, per unit area of the emitting surface that's normal to this direction. And again, I'll show you a picture of this. Per unit wavelength interval around lambda, and per unit solid angle around the direction. Okay, so let's write that down and then try to break it down a little bit. So the rate at which radiant energy is emitted at a specific wavelength, lambda, in the direction defined by theta and phi, so in the theta phi direction, per unit area of the emitting surface normal to this direction, per unit wavelength interval d lambda about lambda, per unit solid angle about this direction. So radiation depends on, or is a function of, wavelength and direction. So this is just saying it's a rate for a specific wavelength in a specific direction. And then, because we talk about fluxes typically with radiation, it's per unit area. And then per unit wavelength interval about lambda and per unit solid angle about this direction. And this just comes about, this per unit wavelength interval and per unit solid angle, because that comes about because we have to integrate up over all of the wavelengths in all of the directions. And so to do that, you basically add up across all of the wavelengths. So if you're doing that discretely, you could like bin all the wavelengths up and say we're going to add up across all of these. But for integration, you say that your bins are just infinitesimally small. So that's why you have this per unit wavelength interval about lambda and per unit solid angle about this direction. So that's just saying that you're going to integrate up over those differentially small kind of bins of wavelength and direction. And for intensity, the per unit surface area is per unit area of the emitting surface that's normal to the direction of emission, which is a little different from our typical surface area definition. So here's kind of what that looks like. It's basically just the projected area of dA1 in the direction of emission. So we have radiation being emitted in this direction defined by theta and phi. And for radiation intensity, it's per unit surface area of this, the surface area dA1 projected in the direction of emission. And that works out to be dA1 cosine theta.
Is the eye radiating that?
No.
Or is that going
The point of the weird looking eye is to show you that this is what it would look like. This is what dA1 would look like if you were looking at it from the same direction as of radiation. Yeah.
Okay.
It's not like super necessary.
Right. But the source of radiation would be in that.
The source of radiation is this dA sub 1. Yeah, so that's the radiating surface. Okay. Is that moderately clear? All right.
Kind of one more. Yes, no?
Yeah?
So it's only radiating kind of in that one direction then?
So we are, right now, we're just talking about consider radiation in one direction at one wavelength. And then we'll integrate up over all of the directions and all of the wavelengths to capture all of the radiation. So this is just saying, okay, we're just considering one case where it's one wavelength going in one direction to define spectral intensity. And then we integrate spectral intensity over all of the wavelengths and all of the directions to get the total emission. Okay. Radiation is different. Okay. All right, so the component, what we just showed, the component of dA1 normal to the direction of radiation is dA1 cosine theta. So now we can write down mathematically our definition of spectral intensity. So remember, we're talking about the rate of emission for one wavelength in one direction that's defined by these theta and phi angles. So that's defined as this differential rate, the rate at which radiation is emitted from the surface, per unit area of the emitting surface normal to the direction of radiation, which we said was dA1 cosine theta, per unit wavelength interval around lambda, and per unit solid angle around this direction. So that's the mathematical definition of radiation intensity. Spectral intensity, sorry. And it's going to have units of watts per meter squared steradian micrometer, which just comes from Q is a rate of heat transfer, so watts meter squared steradian micrometer. So we typically want to know the total rate of emission, the emissive power, which we've talked about previously, capital E. And to find that, we integrate the spectral intensity up over all of the wavelengths and all the directions. But to do that, we need to know how to calculate the spectral intensity. So we're going to talk about calculating the spectral intensity a little bit later. And right now we're going to go into the mathematical definitions of the total emissive power and then go through the similar thing for radiation, or for irradiation and radiosity. Okay, so now let's just say given spectral intensity, we can calculate the emissive power. Which is this quantity E that we've talked about before. So first we'll calculate the spectral emissive power. E sub lambda. So hopefully you can guess what this is. We're just going to take the spectral intensity, which is a function of wavelength and direction, and integrate up only over all of the directions. So then that gives us the spectral emissive power, which is the rate of emission for one given wavelength in all of the directions. Okay, so the spectral emissive power, rate of emission in all directions for a given wavelength again per meter squared and unit wavelength. So basically just taking the spectral intensity, integrating up over the directions. So we still have a function of wavelength, but no longer a function of direction. So we showed earlier to integrate up over the angles that define a hemisphere, we go from 0 to 2 pi and 0 to pi over 2. And then integrate the spectral intensity and then integrating up over the area. And so now we've removed the dependence on the steradian. And now this is just per unit surface area of the emitting surface per unit wavelength interval. And the one kind of odd thing about this, the way it's defined, is the spectral intensity is defined as the per unit surface area of the surface dA1 normal to the direction of emission, whereas the spectral emissive power is just per unit surface area. So that's where this cosine theta, that's why this is in the integrand here. All right, so the next thing we're going to do, you can probably guess, total emissive power. So we integrated up over all of the directions, and now we're going to also integrate up over the wavelengths. So integrating from 0 to infinity of the spectral emissive power. And this leaves us with the total emissive power in watts per meter squared. So we'll say this is the rate of emission per unit area at all wavelengths and in all directions. Okay, a special surface which can be used to approximate a lot of real surfaces is the diffuse emitter. And this simplifies the problem a little bit because diffuse emission is independent of direction and only depends on wavelength. So for a diffuse emitter, the spectral intensity is now just a function of wavelength. And this simplifies the integration. So now the spectral emissive power is just pi times the spectral intensity. And the total emissive power is pi times I sub e, where this is just the total intensity rather than the spectral intensity. So it's convenient to approximate surfaces as diffuse emitters when we can, because we don't have to account for the directional effects. Okay, so that's it for emission. We started by considering the fact that we have radiation in one direction at one frequency, and then we integrate that up over, at one wavelength, and then we integrate that up over all directions and all wavelengths to get the total emissive power. Okay, so these same concepts apply to irradiation. With just a little bit of tweaking. So we'll go through that a little more quickly since we kind of already laid the groundwork for it. So the spectral intensity of irradiation. So now we're talking about radiation that is received by a surface rather than emitted by a surface. So the only difference here is we have this I, so irradiation rather than emission. And so this is, instead of writing out the whole gigantic definition, we'll say this is similar to spectral intensity of emission. Except we're considering radiation incident from the theta phi angle rather than emitted in the theta phi angle. And it's per unit area of the intercepting surface that's normal to this direction, rather than per unit area of the emitting surface that's normal to this theta phi direction. So just like with emission from the spectral intensity, we can get spectral irradiation. So same idea, we just integrate up this intensity over the area. Same thing for total irradiation. Integrate up over the wavelengths. And then if the irradiation is diffuse, So very similar, except now we're just basing our analysis off of the received radiation. So from the angle that it's received and the surface area perpendicular to that angle of the receiving surface. Okay, questions about anything so far? I believe, I would have to go back through the math, but I think that this is pi instead of 2 pi because it's based on the surface area, the actual emitted or received surface area, rather than the surface area perpendicular to the direction of emission or reception. Because if we're integrating up over a hemisphere, that's 2 pi steradians. So I think it's because the relevant area is the surface area for the spectral and total irradiation rather than the intensity. Okay. Last thing, we're just going to write down these definitions for radiosity. Again, very similar. If you remember, radiosity accounts for all radiant energy leaving a surface. For an opaque surface, which we typically restrict our analysis to, this is emission and reflection. So incident radiation can be absorbed, emitted, transmitted, or reflected. For an opaque surface, there's no transmission. So the total radiant energy leaving a surface will be, for an opaque surface, emission plus just reflection. So we had spectral emission, spectral irradiation, spectral radiosity. And that's from integrating the intensity up over the angles. But now this is the intensity of the emission and reflection. The same unit, watts per meter squared micrometer. And this I lambda E plus R is the spectral intensity for emission and reflection. And then total radiosity. We should have this down by now. Integrating the spectral radiosity up over all of the wavelengths. And then finally, for radiosity, we're considering emission and reflection. So for the diffuse case, the surface has to be both a diffuse emitter and reflector. So if the surface is a diffuse emitter and reflector, the spectral radiosity is pi times the spectral intensity for emission and reflection. And the total radiosity is pi times the total intensity for emission and reflection. So just like before. All right, any questions on that? And then based on these definitions, we know the net radiative flux is everything that leaves versus everything that is incident, so J minus G. So you can get the definition for the net radiative flux as well from everything that we've written down. Okay, so to actually perform any of these calculations, you need to know what the spectral intensity is, the I sub lambda I E E plus R. And the way we're going to calculate the spectral intensity is first by introducing the concept of black body radiation. So we talked about black bodies a little bit when we first introduced radiation, and we said they're basically the perfect emitters and absorbers of radiation. So we're going to talk about black bodies, and then we're going to compare real surfaces to black bodies as a way to calculate the spectral intensity of real surfaces. So let's write down a couple things about black body radiation. So we know that black bodies absorb all incident radiation, regardless of the wavelength and direction that it's incident from. So absorb all incident radiation. For a given temperature and wavelength, no surface can emit more energy than a black body, so it's a perfect emitter. And then finally, black bodies are diffuse emitters. So the radiation that they emit is independent of direction. Okay, we'll stop there, pick back up on Monday. One announcement, I will be at a conference on Tuesday. Abby and Shin are unavailable, so we're going to cancel recitation. I will post problems, sample problems, and if you all have questions, I'm happy to take some lecture time to go over them. We'll still have the room, so if you all want to come and work on your labs here, that's perfectly fine. And have a good weekend.